Welcome back, everyone, to another deep dive. Today, we're going to try to answer a question I think we've all pondered at some point. What makes things stay put?
Yeah.
Like, why doesn't everything just fall apart?
It's a pretty fundamental question when you think about it.
Yeah. And today, we're diving deep into the world of rigid body equilibrium to find out. I mean, think about it. How do skyscrapers stand tall? How do bridges support tons of traffic?
Well, the principles we're going to be exploring today are really at the heart of answering those questions.
Yeah, I think this is going to be a good one. So to get us started, you went through Chapter 5 of Statics textbook.
Right.
And our goal today is to pull out the core concepts from the first 6 sections. Really get a grip on what makes a rigid object stable and how we analyze the forces and moments acting on it, but without getting bogged down in the formulas.
Yeah, exactly. So really focusing more on the concepts and the big ideas rather than getting too lost in the equations themselves.
Yeah, but basically think of this as your conceptual toolkit for understanding structural stability.
I like that.
Okay, let's get started.
Sounds good.
So the first concept we're going to unpack is this idea of degrees of freedom. Now, when we talk about a simple particle, its movement is pretty straightforward, right?
Right.
You can just move from one point to another in space.
Yeah, just a simple translation.
Exactly. But a rigid body, like, let's say the phone in your hand, is a different story. What's the key distinction there?
Well, the big difference, as you hinted at, is that rigid bodies can rotate. It's not just about their position, they also have an orientation, which introduces this idea of degrees of freedom, which basically refers to the number of independent ways that an object can move.
So think of it as like the menu of possible movements.
Like that analogy.
All right, so let's try to visualize this. Imagine a flat object, like a piece of cardboard, lying flat on a table. How many different ways can it move independently in that two-dimensional space?
Okay, so in 2 dimensions, a rigid body has 3 degrees of freedom. It can slide left or right. That's what we would call movement along the x-axis. It can slide forward or backward, movement along the y-axis. And then crucially, it can also rotate within that plane. So that would be rotation around the z-axis.
So it's got like 3 independent controls for its movement on that table.
Precisely. And figure 5.1.1 in the textbook actually illustrates these 3 possibilities really well.
Cool. So now, stepping out into the real world, going to 3 dimensions, like let's say that book we were talking about holding earlier, what happens to the number of possible movements?
Okay, so going to 3 dimensions adds more possibilities to that menu of movements. Now, the object can move along the x, y, and z axis, so that's like forward and backward, left and right, and then up and down. And it can also rotate around each of those 3 axes. So that gives us a total of 6 degrees of freedom, 3 ways to translate and 3 ways to rotate. Figure 5.2.2 shows this.
Now, here's where it gets interesting. For something to be in static equilibrium, meaning it's not moving or rotating at all,
Yeah.
what needs to happen to all of these potential movements?
Well, all of them need to be restrained. Every single degree of freedom has to be held in check by some kind of support or constraint. If even one of those potential movements isn't restricted, then the object is unstable. It's free to move in that way.
So it's like a chair with one leg shorter than the others.
Yeah,
It's unstable. It's going to wobble until all of those movements are somehow restrained.
exactly.
And this source actually talks about the importance of stability, especially in engineering, and mentions the use of something called redundant restraints. What's the idea behind that?
Well, redundant restraints are essentially extra supports. So beyond the minimum number that you would need for stability, it's basically a safety measure. So you can imagine a bridge, for example. Engineers might use more supports than are theoretically required just in case one of those supports fails.
Yeah, so it doesn't just immediately collapse. The others can still provide that necessary restraint.
Exactly, building in that safety margin.
Now, what's fascinating to me is this balance between having enough restraints for stability and then having too many. And the source mentions that too many restraints can lead to a system being what's called indeterminate. What does that mean in a practical sense?
So indeterminate basically means we can't uniquely solve for all of the reaction forces and moments using just our equilibrium equations. It might still be a stable structure, but figuring out exactly how the forces are distributed among those supports becomes a lot more complex. It often requires more advanced analysis techniques.
Okay, so we know about restraining movement, but how do we actually figure out what these restraining forces are? And that leads us to section 5.2 and the concept of the free body diagram,
Yeah.
which is often shortened to FDD.
Right.
This sounds like a pretty crucial tool.
Absolutely. The textbook actually really emphasizes that drawing a correct free body diagram is the very first and most important step in solving any equilibrium problem. Because it's like creating a clear picture of all the external influences that are acting on the object we're interested in. If you get that picture wrong, then any calculations you do afterward are meaningless.
Garbage in, garbage out, as they say.
Exactly.
Okay, so how do we go about creating this all-important FBD? The source lays out 5 key steps, so let's walk through those steps. The first one is to select and isolate the object. What exactly does that involve?
Okay, so that's where you essentially separate, either mentally or on paper, the object that you're analyzing from everything else that it's connected to. So it supports any other objects around it, and you're basically drawing a sketch of just that object floating in space by itself.
All right, step 2 is to select a reference frame. So setting up our X and Y and Z, if needed, axes. Why is this step so important?
Well, this is all about making things easier for ourselves down the line. If you choose a smart reference frame, it can really simplify your calculations. For example, if you have a force that's acting at a known angle, you might decide to orient one of your axes along that force, so you don't have to break it into components later.
Right, just working smarter, not harder.
Exactly.
All right, step 3 is to identify all loads.
Yeah.
And this is where we start adding in those forces acting on our isolated object. What kinds of loads are we typically looking for here?
So anything external that could cause the object to move or to rotate. So this could be a direct push or pull. It could be the weight of the object itself acting downwards due to gravity. It could even be something called couple moments, which are basically pure rotational forces. And we're going to represent each of these loads with a clearly labeled arrow, or if it's a moment, a curved arrow on our diagram.
And then we come to step 4, which is to identify all reactions. This sounds like it might be the trickiest part. What are these reactions that we need to account for?
So reactions are the forces and or moments that were being provided by the supports that we removed back in step 1. They're what was keeping the object in equilibrium in the first place. So for example, if an object is sitting on a table, that table is exerting an upward reaction force on the object. Or if something is attached to a wall with a hinge, that hinge is providing both horizontal and vertical reaction forces to keep it from moving.
So you have to kind of think in reverse and replace each support with whatever kind of force or moment it was preventing.
Exactly. And figures 5.2.1 and 5.2.2 in the textbook actually show some really common types of supports and the reactions that they exert, which can be super helpful when you're first learning this.
Yeah, that visual aid is definitely key for wrapping your head around it. All right, and finally, step 5 is to label the diagram. What kind of information are we including in those labels?
Okay, so we need to label all of our forces and moments, both the applied loads that we identified in step 3 and the unknown reaction forces and moments from step 4. Include their magnitudes if we know them, their directions, and then any relevant dimensions or angles on the diagram.
So really just create that full visual picture of the problem.
Exactly.
Awesome. All right, so once we have this free body diagram all drawn up and labeled correctly, what's the next step in analyzing equilibrium? And that takes us to section 5.3, which is the equations of equilibrium.
Right, so the free body diagram is our blueprint. And now the equations of equilibrium are the math rules that govern the whole situation.
Okay.
So in statics, since we're dealing with things that aren't accelerating, we have 2 fundamental vector equations. The first is that the sum of all forces acting on the body must equal 0.
That's often written as like sigma F equals 0.
Right. And then the second is that the sum of all moments about any point must also equal 0. So sigma m equals 0.
So basically these equations are just saying that everything's balanced, there's no net force that's causing translation, and there's no net moment causing rotation.
Exactly. Everything's in perfect harmony.
Nice. And we can actually break down these vector equations into simpler scalar equations, right? One for each direction.
Right. So in 2 dimensions, the sum of forces equals 0 breaks down into 2 scalar equations. The sum of forces in the x direction equals 0, and the sum of forces in the a direction equals 0. And for the moments, we typically just have one scalar equation, which is the sum of moments about some point in that 2D plane equals 0. And then, of course, if we're in 3 dimensions, we would have 3 force equations and 3 moment equations.
And the source mentions that the number of equations we need depends on those degrees of freedom that we talked about earlier. How does that connection work?
So for a body to be in equilibrium, we need at least as many independent equilibrium equations as we have degrees of freedom that need to be restrained. So in 2D, we have 3 degrees of freedom, so we typically use 3 independent equilibrium equations. And then in 3D, where we have 6 degrees of freedom, we need 6 equations.
Makes sense. Okay, so let's focus a little bit more on the 2D case now from section 5.4. The textbook says that we usually use those three equations. So sum of forces in x equals 0, sum of forces in y equals 0, and then sum of moments about a point A equals 0. But it also mentions that we have some flexibility in choosing these equations. How so?
Yeah, that's a really important point. So while that set of equations is a common starting point, it's not the only option. You could, for instance, replace one of the force equations with another moment equation. So maybe take the sum of moments about a different point B. As long as the three equations you choose are what's called linearly independent, meaning one isn't just a combination of the other two, then they'll give you the same information.
That's handy. Does the source give us any tips on how to choose these equations wisely so that it makes solving the problems easier?
Yeah, it does. One of the key strategies is to pick the point about which you're taking moments very strategically. So the textbook actually highlights that if you take moments about a point where two or more unknown forces intersect, then those forces won't show up in your moment equation at all because their lever arm is 0. So that can simplify things considerably. Sometimes you can even get an equation with just one unknown.
That's a really good shortcut. Any other advice on setting up and solving these 2D equilibrium problems in the most efficient way?
Yeah, aligning your coordinate system with unknown forces, if possible, can simplify things. And then the textbook also emphasizes the importance of solving any equations that have just one unknown first, because once you find that unknown value, you can plug it back into the other equations to make them simpler.
Right, like a domino effect.
Exactly. And
Yeah.
example 5.4.1 in the textbook actually demonstrates this beautifully. It solves the same problem in multiple ways, showing the efficient approaches and the less efficient approaches.
Nice. Okay, so moving on now to section 5.5 and 3D rigid body equilibrium.
Mm.
The source points out that while all the basic principles are the same, things do definitely get more complicated. What are the main challenges we run into when we're dealing with equilibrium 3 dimensions?
Well, the biggest challenge is that you have more degrees of freedom to account for, and it's also just harder to visualize the forces and moments when you're working in 3D space. Now you can have up to 6 unknown reactions, and the moments are no longer just about clockwise or counterclockwise rotation.
Right.
You have moments that can cause rotation around all 3 axes.
Right. The source also mentions that 3D problems often rely on vector algebra. Why is that the case?
Well, vector algebra, specifically something called the cross product, becomes super important here because it allows us to elegantly handle both the direction and the magnitude of the moment that's created by a force acting at a particular position. In 2D, we could often just multiply a force by a distance with a plus or minus sign for direction. But in 3D, where forces and positions have x, y, and z components, the cross product automatically gives us the resulting moment vector.
And when we're summing moments in 3D, it's not just the moments caused by forces anymore. The source mentions something called applied couple moments.
Right, so in 3D, you have to consider both those moments that are generated by forces, which you calculate using the cross product, and any externally applied couple moments that might be acting on the body.
What are those couple moments again?
They basically cause rotation without any net force.
Got it.
So you essentially have to sum up all of these moment vectors about a chosen point and set that total equal to 0 for rotational equilibrium.
And solving these 3D equilibrium problems can result in, oh gosh, up to 6 equations with 6 unknowns. The source says linear algebra can be a really valuable tool here. Why is that?
Well, when you have a system of linear equations, which means your unknowns aren't raised to powers or inside trig functions or anything like that, linear algebra gives us a systematic way to solve for all of those unknowns simultaneously. So it's much more efficient than trying to solve those equations by hand.
Okay, and finally we reach section 5.6, which deals with stability and determinacy. Now, we touched on stability earlier when we were talking about degrees of freedom, but how does the source define it more formally?
So the source says that a stable, rigid body is basically one that is sufficiently supported so that it can prevent any translation or rotation, no matter what loads are applied to it. And importantly, stability is a property of the supports themselves, not the specific loads that are acting on the body. So an unstable body, like if you imagine a tripod that only has 2 legs, it's inherently unstable no matter what you put on top of it.
Right. And then there's determinacy. How do we figure out whether we can actually solve for all those unknown reactions using just our basic equilibrium equations?
So a system is statically determinate if the number of independent equilibrium equations that we have is equal to the number of unknown reaction components. If that's the case, then you should be able to solve for everything. But if you have more unknowns than equations, then the system is statically indeterminate, as we talked about before. And if you have fewer equations than unknowns, then the system is usually unstable.
All right. And here's where it gets interesting. The source actually gives us some quick checks for assessing stability and determinacy, specifically in 2D systems. Can you walk us through those?
Absolutely. The first rule of thumb is to simply count the number of reaction components that you have in your free body diagram. For a 2D system, if you have exactly 3 reaction components, that usually indicates a statically determinate system. If you have fewer than 3, that often means it's unstable. And if you have more than 3, it's usually indeterminate.
Okay. What's the second check for 2D systems?
So the second thing to check is the direction of your reaction force components. If all of those forces are parallel to each other, then the system is probably going to be unstable for translation in the direction that's perpendicular to those forces. So imagine a beam that's only supported by rollers that are providing vertical forces. That beam is free to move horizontally.
Right. I could just slide right off those rollers.
Exactly. And then the third check is to look at the lines of action of all your reaction forces. If all of those lines of action intersect at a single point, then the system is likely unstable for rotation about that point.
So like a door hanging by only one hinge.
Exactly. It's going to swing open.
All right, so those are really helpful rules of thumb. So just to wrap up this deep dive into rigid body equilibrium, we've covered a lot today. We've talked about degrees of freedom, the crucial role of those free body diagrams, the equations of equilibrium in both 2D and 3D, and some valuable checks for stability and determinacy. So hopefully this has given everyone a solid foundation for understanding how things stay put in the world around us.
Absolutely. And it's really fascinating to me how these principles, which can seem kind of abstract when you're first learning about them, actually underpins so much of our built environment and the technology that we use every day.
Yeah, absolutely. It's all around us, from the chairs we sit on to the bridges we cross. It all comes down to applying these concepts correctly.
It really does.
So this kind of leads to a question for everyone listening. Now that you have a better understanding of stability and determinacy, can you start to look at everyday objects and structures and intuitively assess how they're supported? What might make them stable or unstable? What do you think?
That's a great question to ponder. And of course, this was just an introduction. There's a lot more we could delve into, especially when we start talking about things like indeterminate systems and 3D equilibrium. Those could definitely be topics for future deep dives.
I think they definitely could. But for now, that's going to wrap it up for today. Thanks for joining us on this deep dive into rigid body equilibrium. We hope you found it insightful.
Thanks for having me.
And we'll catch you in the next one.